On nights when the air is still and the stars are unblinking, there's a quiet rhythm out there that never misses a beat. A rhythm so constant that you could set your whole life to it and it would never falter. Above us, planets are moving, not rushing, not wandering, but gliding along invisible paths they've followed for billions of years. And the strangest thing, they never fall into the sun and they never drift away into the dark. They just stay, as if an unseen hand guides them. It's a mystery we take for granted, but once you start wondering about it, it pulls you in. Why do they stay? What stops them from simply slowing down and falling, or speeding up and escaping into the cold forever? The answer is woven into the very fabric of motion and gravity. And once you see it, you'll never look at the night sky the same way again. So tonight, let's wander quietly through this story. From the earliest days of the solar system to the eternal dance happening above us right now. A dance without music, yet perfectly in tune. A quiet night sky that hides a constant cosmic dance. If you've ever stood outside on a still night, you know the kind, where the air feels like it's holding its breath. You might think the sky is frozen in place, but it isn't. Every point of light is moving, some slowly, some fast enough to cross the heavens in minutes. The planets especially are never still. Even right now, Earth is speeding along its track at about 30 kilometers every second. And yet you feel nothing. No rush of wind, no tilt beneath your feet, just the illusion of stillness. It's like watching a clock where the hands never seem to move until you look away and realize hours have passed. That's the thing about orbits. Their motion so perfect, it disappears into the background. The planets are locked in a dance they don't choose, but can never stop. And the more you think about it, the stranger it becomes. Why don't they fall straight into the sun? Why don't they drift away into deep space? They're not tied by ropes. They're not on rails. And yet they never lose their place. The truth is hidden in forces you can't see, but they're at work every moment. The invisible threads that keep worlds from drifting away. Out there in the black, there are no strings, no chains. But there is a pull. Gravity. It's so quiet you'd never notice it unless something moved. It's the sun's silent handshake with every planet, a constant tug inward that never lets go. You can't see it, but you can feel it if you jump and come back down, or if you drop something and it falls to the floor. In space, that same pull works over millions of kilometers. But gravity alone isn't the whole story. If it was, the planets would have all fallen into the sun long ago. Something else is at play: motion. The planets are not just sitting there, they're moving sideways at exactly the right speed. That speed is what keeps them from plunging in. It's like swinging a ball on a string. Let the string go, and it flies off in a straight line. Keep the string tight, and it moves in a circle. In space, there is no string, only the invisible grip of gravity, balancing the forward rush of motion. It's a balance so precise that even the tiniest change could send a planet wandering. How a planet's fall is forever interrupted by motion. Imagine this. If Earth stopped moving sideways right now, it wouldn't just hover where it is. It would start falling, straight toward the sun, and in about 2 months it would crash into that blazing star. But it never happens, because we are falling already, always falling, but missing. The Earth's forward speed bends that fall into a curve, and the sun's pull keeps bending it, over and over, making a circle that never closes. It's the same reason the moon doesn't crash into Earth. It's falling toward us all the time, but its sideways speed means the ground curves away as fast as it falls. That's the secret of an orbit, an endless fall that never lands. The mind struggles with that at first, falling but not getting closer, moving at tremendous speeds yet feeling still. It's a contradiction that only makes sense when you see the universe as a giant stage where motion and gravity are the choreographers. And this dance is so stable that it's been running since before life began here. The balance point between the pull of gravity and the push of movement. There's a sweet spot for every orbit, a speed that's neither too fast nor too slow. Go slower and you spiral inward, the sun's pull winning the contest. Go faster and you'll slingshot outward, maybe never to return. Each planet, from tiny Mercury to distant Neptune, sits right in its own perfect balance point. And that balance isn't luck. It's the result of how each planet was born, billions of years ago, when the solar system was just a cloud of gas and dust. Bits began clumping together, drawn by gravity. As they grew, they picked up speed, swirling around the young sun. Those speeds became their permanent ticket to orbit. And once space sets you in motion, there's nothing to slow you down. It's this quiet equilibrium that makes our night skies predictable. We can tell you where Saturn will be 100 years from now, almost to the minute. That's how dependable the balance is. But forever in space has its own meaning. Things stay the same for billions of years, yet the seeds of change are always there. Why planets don't spiral into their stars despite the pull? It feels like the sun's gravity should be a trap, a slow spiral inward. But that isn't what happens. Gravity doesn't work like a vacuum cleaner, pulling things in until they're gone. It works more like a leash that keeps the planets from drifting too far. As long as their speed is right, they keep looping around. There's no air to slow them, no friction to bleed away their motion. In the vacuum of space, movement lasts. Think of skating on a frozen lake. If you push yourself and then stop pushing, you'll keep gliding for a long time. In space, there's no ice, but there's also no resistance. A planet's momentum is eternal unless another force interferes. Over vast timescales, tiny influences, the tug of other planets, the pressure of sunlight, can make small changes. But these are whispers compared to the sun's grip. That's why, for the age of the solar system, the planets have held their places like beads on invisible threads. And those threads are just the start. The first spark of movement in a newborn solar system. Long before Earth was blue, before Saturn had rings, there was only a swirling cloud of gas and dust. It stretched wide, thin, and shapeless, with the newborn sun glowing at its center. Within that haze, tiny specks of matter began pulling together, dust clinging to dust, stone to stone, a slow gathering under the gentle insistence of gravity. And as they gathered, something happened. They began to spin. The sun's birth had stirred the cloud into motion, and like water swirling down a drain, the movement spread to everything in its reach. These young clumps weren't yet planets, but their paths were already forming. They circled, collided, merged, but always kept moving. It's strange to think that the path Earth travels now, the exact shape and speed of it, was decided in those chaotic first millions of years. The spark that began then never went out. In space, once motion starts, it doesn't fade. And that first motion still lives inside every orbit today. How swirling clouds of dust became steady travellers. At first, those newborn paths weren't the smooth, perfect loops we imagine. They were messy, stretched out, tilted, crisscrossing one another. Rocks smashed together, shattering and reforming. Some were thrown toward the sun, others flung into the outer dark. But over time, the chaos began to calm. The survivors settled into patterns, each finding a path where they could keep moving without constant collisions. These paths slowly became orbits, the quiet repeating journeys we see today. The planets we know are the ones that found stability. The ones that didn't aren't here anymore. There's a kind of poetry in that, the idea that every planet is a survivor of a billion-year traffic jam. The orbits that remain are the ones that worked, the ones where motion and gravity agreed. And once that agreement was made, the planets became travellers on roads they will follow for ages beyond counting. The hidden role of ancient collisions in setting paths. Collisions sound like destruction, but in the early solar system, they were also sculptors. When a large impact hit a forming planet, it could change its speed, tilt its axis, or shift its orbit entirely. Earth's own moon is likely the result of such a collision, a glancing blow that not only gave us a companion, but also refined our path around the Sun. Some collisions sent planets inward, some outward. Others slowed them down or sped them up just enough to lock into stable positions. The solar system is full of scars from these ancient encounters, craters, tilted rotations, even backward spinning moons. And yet, without those impacts, the balance we see now might never have formed. It's almost as if the orbits we take for granted today were hammered into place by a long ago chaos. A reminder that stability often comes from moments of great upheaval. Why perfect speed matters more than perfect shape. When we imagine orbits, we picture perfect circles. But the truth is, most are stretched ovals, called ellipses. It turns out, shape doesn't matter as much as speed. If a planet's forward speed is exactly right for its distance from the Sun, it will keep circling, whether in a neat circle or a long oval. Change that speed even a little, and the path changes too. Too slow, and the Sun's pull wins. The planet spirals inward. Too fast, and it escapes into the dark. The speed has to be just right. It's a delicate balance, but it's not fragile. Once set, a planet's speed tends to stay the same for billions of years because there's almost nothing in space to slow it down. No air, no ground, just open emptiness. That's why, from Mercury to Neptune, every planet is still gliding at the speed it was given in its youth, the gentle tug that keeps orbits round or stretched. Even in the calm of today's solar system, orbits are never perfectly still. The planets pull on each other. Jupiter's vast mass tugs at Mars, Earth, and even Saturn. Saturn returns the favour. These gentle gravitational nudges can slowly stretch or round out an orbit, shifting its shape over thousands of years. It's a bit like two dancers passing close on a crowded floor. They never collide, but the sway of one subtly affects the other's steps. Over time, these tugs create rhythms, where planets fall into patterns called resonances, their movements quietly linked. This invisible conversation between worlds has kept the solar system stable for ages. It smooths out some paths, elongates others, but always within limits. No planet gets to wander too far, and it's this slow, patient choreography that lets the great cosmic dance go on, night after night. The Sun's silent grip reaching across billions of kilometers. The Sun doesn't just warm our skin or light our days. It holds us. Its gravity stretches far beyond where our eyes can see, a constant invisible pull that reaches to the edge of the solar system and beyond. Even Pluto, so far that sunlight takes hours to arrive, still feels that steady tug. Without it, every planet, moon, and comet would simply drift away. What's astonishing is how even at great distances that grip is strong enough to keep worlds moving in orderly loops. You can't hear it, you can't see it, but it's there. An unbroken connection between star and planet. If you could somehow turn off the Sun's gravity, every planet would instantly fly away in a straight line, like beads thrown from a spinning string. But because that pull never lets go, the dance goes on. And in this dance, the Sun doesn't chase its partners, it simply stands at the centre, and they keep circling. How a planet falls endlessly without getting closer. It's hard to picture, but the truth is, Earth is falling. Every moment, the Sun's gravity is pulling us inward. If we weren't moving forward, we'd plunge straight into it. But we are moving sideways at just the right speed, so instead of hitting the sun, we keep missing it. Over and over, forever. Think of throwing a stone so fast that the ground curves away beneath it at the same rate it falls. That's an orbit, a fall that never ends, a chase where the sun never quite catches its partner. The moon does the same around us. Every second it falls toward Earth, but its sideways speed keeps it aloft, tracing a perfect loop in the sky. This endless falling isn't tiring. There's no friction in space to slow the motion. It's as effortless as drifting in a dream, forever suspended between motion and pull. The strange truth that motion is a kind of escape. It might sound strange, but the very thing keeping planets in orbit, their sideways motion, is also what keeps them from being trapped completely. If Earth moved just a little faster, we'd slip away from the sun entirely, leaving its warmth behind. If we moved slower, we'd spiral inward to destruction. So our current speed is like a fine edge between escape and capture. That's why scientists speak of escape velocity, the speed you need to break free from a world's pull. For Earth, it's about 11 kilometers per second. For the Sun, at our distance, we're already moving at the perfect speed to almost escape, but not quite. In a way, the planets are always trying to leave, but the Sun's gravity keeps calling them back, curving their paths into endless loops. It's not a prison, it's a partnership. Neither side lets go. Why space has no brakes to slow the planets down. Here on Earth, everything eventually stops moving. Wheels slow, balls roll to a halt, people tire. That's because of friction, air resistance, surfaces rubbing, energy turning into heat. But space is a different world entirely. Out there, there's no air, no ground, nothing to push against. A moving planet stays moving unless something big changes its speed. Without brakes, there's nothing to pull a planet inward except gravity itself. That's why the orbits we see today are the same ones planets have followed for billions of years. No cosmic wind slows them, no hidden drag saps their speed. Unless a massive force, like another star passing too close, interferes, they'll keep gliding forever. It's an eerie thought. Motion in space is not a thing you start and stop. It's a thing you join and never really leave. The way orbits remember the past forever. Every orbit is a story frozen in motion. The speed, the distance, the tilt. All of it is a memory of how that planet formed, what collisions it survived, and what gravitational tugs it's felt since birth. Even the smallest wobble can be traced back to something in its past. A near miss, a passing comet, the subtle pull of a neighbour. This means that when astronomers study a planet's orbit, they're reading a history book written in curves and speeds. The solar system is like a library, each orbit a record of billions of years. And the remarkable thing, these records don't fade. As long as the balance between motion and gravity holds, the memory lasts. The path repeats. The story plays again and again. How planets interact like dancers who never touch. Even though space feels empty, the planets are never truly alone. They pull on each other, subtly, constantly. Jupiter tugs at Saturn, Earth nudges Venus, and Mars feels the whispers of them all. These forces are gentle, almost shy, but over centuries they can shift an orbit's shape or tilt. It's a bit like watching skilled dancers on a wide floor. They may never collide, but each feels the presence of the other, adjusting steps without thinking. This silent awareness keeps them moving in harmony. Without these invisible exchanges, orbits might drift into dangerous patterns, leading to close calls or even ejections from the system. Instead, the planets settle into arrangements where their paths weave without crossing. It's a conversation without words, gravity speaking in pauses, motions, and subtle changes. The unseen handshake between Earth and Jupiter. If Earth has a quiet guardian, it's Jupiter. This giant's gravity is so strong that it shapes not only its own moons, but the fates of worlds far away. Asteroids that might wander toward Earth are often pulled aside by Jupiter's influence, captured into harmless paths, or flung out of the solar system entirely. But it's not a one-way street. Earth also affects Jupiter ever so slightly. Each tug is a handshake, a tiny exchange of energy that shifts their motions in ways so small, only precise instruments can detect them. Over millions of years, these handshakes help keep orbits stable. Without Jupiter's balancing role, the inner planets might face more chaotic changes. It's humbling to think that a world 500 million kilometers away is part of the reason our orbit is so steady today. Why the moon's pull keeps Earth steady in its place. While Jupiter's influence is vast, Earth's closest partner is the moon. The moon's gravity doesn't just raise tides in our oceans, it also steadies our planet's tilt, keeping our seasons predictable. Without it, Earth's axis might wobble wildly, causing dramatic climate shifts over short timescales. This stability also affects our orbit. A steady tilt means our path around the Sun doesn't change erratically, which helps keep life-friendly conditions over long periods. In return, Earth's gravity keeps the Moon close, slowing its escape into space over billions of years. The two are locked together in a slow, graceful spiral outward. It's a relationship of balance, not control, where each shapes the other's journey through the solar system. The subtle push of sunlight that can bend a path. It might seem impossible that light, with no weight, could change a planet's orbit, but it can. Photons from the Sun carry momentum, and when they hit a planet or asteroid, they give a tiny push. For massive planets, this effect is negligible, but for small objects, sunlight can gradually shift their paths, a process called the Yarkovsky effect. It's so subtle that it might take centuries to notice, yet over long enough times, it can steer an asteroid away from or toward a planet. Even planets feel an infinitesimal version of this, a reminder that every form of energy in the universe, no matter how soft, leaves a fingerprint on motion. Sunlight warms, it lights, and in the quietest way, it moves things. How even tiny particles obey the same law as planets. From the mightiest planets to the smallest grains of dust, the rules are the same. A particle drifting near the Sun will find itself caught between gravity and its own motion. If its sideways speed is right, it will orbit just like a world. If not, it will spiral inward or escape outward. Astronomers have observed rings around planets, Saturns, Jupiters, Uranuses, made entirely of such particles, each moving in a perfect balance between pull and speed. The same geometry that keeps Earth in its orbit holds those grains in place. It's a comforting thought. Whether grand or tiny, everything in the cosmos moves by the same laws. There is no favoritism, no exceptions. The role of inertia in cosmic choreography. There's a quiet partner to gravity that most people forget about. Inertia. It's the tendency of a moving object to keep moving in the same direction at the same speed unless something changes it. Out in space, where there's no air to slow you down and no walls to stop you, inertia is almost absolute. A planet moving around the Sun isn't constantly pushed forward. It doesn't need to be. Once it started moving billions of years ago, inertia kept it going. Gravity curves its path, but inertia keeps it from falling straight in. It's like tossing a ball across a frozen lake. It keeps sliding because nothing is there to stop it. In space, that slide can last forever. Inertia doesn't speak loudly, but without it, no orbit could exist. How Newton's insight unlocked the secret of orbits. For thousands of years, people could see that planets moved in patterns, but they didn't know why. Then in the 1600s, Isaac Newton realized that the same force that pulls an apple to the ground also keeps the moon in the sky. His law of universal gravitation explained that every mass pulls on every other mass, and that motion plus gravity equals an orbit. Newton's work gave us the math to predict where planets would be centuries into the future. It showed that orbits aren't magic, they're the natural outcome of simple universal rules. What's remarkable is how those rules apply to everything, from planets to satellites to the tiny specks of dust in Saturn's rings. Newton didn't just explain the past, he gave humanity a way to see the future of the cosmos. Why planets seem weightless despite their mass. Earth is massive, over 6 sextillion tons, yet in space it feels no weight at all. That's because weight is the feeling of being pulled against something solid, like the ground beneath your feet. In orbit, there's no floor to press against. A planet is in constant freefall around its star, and that falling cancels the sensation of weight. This is why astronauts feel weightless even though gravity is still pulling on them. They're falling with the spacecraft, just as the spacecraft is falling around the Earth. Planets are doing the same thing, but on a grander scale, falling around the sun forever, never hitting it, never stopping. It's a kind of cosmic suspension, where motion and gravity create a perfect illusion of stillness. The hidden geometry that keeps paths predictable. Every orbit has a shape, and that shape follows precise rules. Kepler discovered that planets move in ellipses, not perfect circles, with the sun at one focus. This geometry means a planet's speed changes slightly along its path, faster when closer to the sun, slower when farther away, yet the overall journey stays predictable. This is why we can forecast eclipses, alignments, and transits centuries in advance. The geometry is so exact, it acts like a blueprint for the solar system's future. It's almost like the planets are following grooves carved into space itself, invisible tracks laid down by the laws of motion and gravity. And the more we understand those tracks, the better we can read the story of our cosmic neighborhood. How time itself is written into every revolution. Every orbit is also a clock. One trip around the sun marks a year for Earth, a little over 88 days for Mercury, and nearly 165 years for Neptune. The length of these years is no accident, it's the direct result of distance and speed. These orbital clocks keep perfect time over eons, ticking away without gears or batteries. Even ancient civilizations used the motions of the planets to mark seasons, plan harvests, and guide navigation. It's humbling to realize that our concept of time is tied to this endless dance. Every calendar page, every birthday, is really a reminder of where Earth is in its path, why no two orbits are truly identical. Even in the most orderly system, there are no perfect copies. Each planet's path is shaped by its distance from the sun, its speed, its tilt, and the subtle tugs it feels from every other object. Even if two worlds seem to move alike, tiny differences would grow over time, making their journeys unique. It's like snowflakes falling through the air. From far away they may look the same, but up close, each has its own pattern. In the solar system, no two orbits are an exact match. These differences don't break the harmony, they create it. Each planet's individual rhythm keeps it from colliding with its neighbours, giving the system balance. It's a reminder that perfection in space is not sameness. It's a blend of differences working together. The hidden wobbles that come from cosmic neighbours. A planet's orbit might look smooth on paper, but in reality, it's full of tiny sways and shifts. These wobbles come from gravitational nudges by other planets. Jupiter's vast mass can pull Mars slightly off course, while Venus can do the same to Earth. Over centuries, these small pushes create patterns, oscillations in the shape and tilt of a planet's path. Astronomers can even detect unseen worlds around distant stars, by watching for such wobbles in the star's motion. It's like seeing a dance partner's slight lean and knowing someone else is guiding their steps. Though they're small, these wobbles are clues to the deep connections between everything in the system. Even the most stable orbit is never perfectly still. It's alive with motion beneath the surface. How a distant planet can shift another's path. Gravity doesn't fade into nothing quickly. It stretches across vast distances. That means even a planet hundreds of millions of kilometers away can influence another's orbit. Sometimes, these influences happen in cycles, where two planets meet in the same relative position again and again, creating a kind of repeating tug. Over millions of years, these repeated pulls can shift the shape of an orbit, making it more circular or more stretched. They can even change the tilt of a planet's rotation or cause moons to drift into new positions. It's a slow, patient process, one that works like water shaping stone. You don't notice it day to day, but given enough time, it leaves its mark. In this way, every planet is both a traveller and a guide to others. Why the solar system moves like a living organism. When you step back and watch the planets as a whole, the solar system feels less like a set of separate worlds and more like a single connected being. Each orbit responds to the others, adjusting in tiny ways that keep the overall structure stable. The sun's gravity is the heart, pumping energy into every motion, while the planets are like organs working together without ever touching. This living quality comes from the constant exchange of momentum, an unseen flow that moves between worlds, moons, and even the smallest particles of dust. It's a reminder that in space, nothing is truly isolated. The motion of one affects all. And this shared motion is why the solar system has stayed in balance for billions of years. The slow drift that happens over millions of years. Despite the stability we see in our lifetimes, nothing in space is truly fixed forever. Over millions, even billions of years, planetary orbits slowly shift. Some move slightly closer to the sun, others drift away. These changes are caused by the accumulated effects of gravitational pulls, light pressure, and even the distant tug of the galaxy itself. The shifts are so slow that no human will ever notice them firsthand, but in the cosmic clock, they are significant. Someday the orbits we know now will be different, and the solar system's pattern will have evolved into something new. It's a quiet reminder that even the most perfect balance is part of a larger, ongoing story. The rare moments when orbits break their patterns. Most of the time, planetary orbits are as steady as a heartbeat. But in rare moments, perhaps once in tens or hundreds of millions of years, something happens to disrupt the balance. A wandering asteroid might pass too close, or a large comet could sweep through the inner system. Sometimes even a small gravitational nudge, given in just the right way, can push a planet into a new path. These events are rare because the solar system's distances are vast and its harmony is strong. Yet when they occur, they can rearrange entire regions of space. Moons may shift, orbits may stretch, and sometimes objects can be ejected altogether. It's a reminder that even in the quietest dance, there are moments when the music changes suddenly. And when it does, the solar system remembers the change forever. How rogue asteroids can change the cosmic map. Not all asteroids are fixed in place. Some wander like drifters, crossing paths with planets. If one passes close enough, its gravity can give the planet a tiny push, or take a little energy away. The change may be minuscule, but over millions of years, that small alteration can shift an orbit's shape or timing. In some cases, these interactions work the other way. The planet changes the asteroid's path, sending it into a new orbit or ejecting it from the solar system entirely. It's a constant exchange of energy, invisible to the eye, but powerful in effect. Over time, such encounters help shape the architecture of the solar system. deciding which paths survive and which are erased. And it all happens without sound in the deep quiet of space. Why some planets may be stolen from other stars. It's possible that not every world in the solar system was born here. When stars pass close to each other in the galaxy, a rare but not impossible event, their gravity can tug planets away from one system and into another. If the timing and speed are just right, a planet from one star can be captured into the orbit of another. Astronomers believe this might have happened in the distant past, not just here, but across the galaxy. Rogue planets drifting alone between stars could be captured and given new homes. If such a thing happened here, the planet's orbit might seem unusual, tilted, stretched, or moving in ways that don't match the others. It would be a stranger in the family, yet still bound to the sun's pull. And in that, it would follow the same rules as every other world, motion and gravity, forever entwined. The quiet fate of worlds in binary star systems. Some stars are not alone. They have a companion star, orbiting together in a shared center of gravity. For planets in such systems, the balance is more complex. A world might orbit one star closely, while both stars orbit each other. Or it might circle both stars at once, tracing a path that must account for the gravity of two suns. In these systems, stability can be fragile. A slight change in one star's motion could disrupt a planet's path entirely. And yet, many such systems exist, with planets keeping perfect time despite the challenges. It's a testament to how adaptable orbits can be, finding harmony even in situations that seem chaotic. And it makes our own single-star system feel simple by comparison. How our sun's life cycle will one day end the dance. The sun feels eternal to us, but it's a star with a lifespan. Billions of years from now, it will swell into a red giant, its outer layers expanding past Mercury and Venus, and perhaps even touching Earth. The change in mass and size will alter its gravity, loosening its hold on the outer planets. Some worlds will drift outward into wider orbits. Others may be swallowed entirely. The graceful loops we see today will vanish, replaced by new paths or emptiness where worlds once moved. It's a sobering thought, but also a reminder that nothing in the universe is truly fixed forever. The cosmic dance we watch now is just one chapter. Why even chaos in space follows hidden order. From far away, the motions of planets might seem perfectly smooth, but zoom in and you'll see ripples. Small gravitational pulls, passing asteroids, and shifting tides of light all stir the orbits ever so slightly. At first glance, this feels like chaos, unpredictable and unruly. But look longer, and patterns emerge. Even in apparent disorder, the same rules apply, shaping the movement with invisible boundaries. Astronomers call this deterministic chaos, the idea that small differences can grow into large effects, yet still follow the laws of physics. In other words, chaos in space is never lawless. It's more like jazz than noise, improvisation built on a steady rhythm, and that rhythm is written by gravity, the quiet composer of the cosmic score. The self-correcting nature of gravitational balance. In many cases, when orbits are disturbed, they find a way back to stability. This happens because gravity works like a restoring force. If a planet is nudged slightly closer to its star, its speed increases, pulling it back into a safer, more distant loop. If it drifts outward, its speed slows, letting gravity pull it back in. It's as if each planet carries an invisible leash, not rigid, but elastic, that stretches and contracts to keep it from straying too far. This self-correcting nature is one reason our solar system has lasted for billions of years without planets colliding or escaping. The system breathes, it flexes, and yet it endures. How planets avoid colliding despite close calls. With so many worlds moving at high speeds, it seems a collision would be inevitable, yet it almost never happens. That's because the distances between planets are vast, and their orbits are carefully layered, like lanes on a highway. Even when their paths seem to cross from our perspective, they're actually separated by millions of kilometers. Resonances, repeating patterns in their orbits, also help. These patterns keep planets from meeting in the same place at the same time, preventing dangerous encounters. It's a silent coordination, built over eons, where each world knows the timing of all the others. And so, the dance continues without a single misstep. Why small changes can echo for eternity. In space, there's no such thing as a harmless nudge. A tiny change in a planet's speed or position, so small it might go unnoticed, can set off a chain of effects that last forever. Over millions of years, that change might grow into a completely new orbit, altering the entire system's balance. Astronomers call this sensitivity to initial conditions, and it's one of the reasons predicting far future orbits can be tricky. The smallest influence today can rewrite the story tomorrow. It's a humbling truth. Even in the most stable systems, nothing is beyond change. Every moment leaves a trace, and every trace can last as long as the stars themselves. The mystery of stable chaos in celestial motion. There's a strange paradox in orbital mechanics. Chaos can be stable. This means a planet's path might change slightly, wobble unpredictably in the short term, yet still remain secure over the long term. Its overall position stays bound to the star, even as the fine details shift endlessly. It's like a candle flame flickering in the wind. The shape dances and changes, but the flame itself stays lit. In the solar system, stable chaos allows for variety without collapse. Some moons of Jupiter and Saturn live in this state, their orbits always shifting yet never breaking free. Even parts of Earth's path have this hidden flicker. It's proof that the universe doesn't need perfect order to last forever. How orbits keep time better than clocks. Long before humans built mechanical clocks, the sky kept time for us. Every orbit, whether of a planet around a star or a moon around a planet, is a cycle that repeats with incredible precision. Earth's year is so consistent that even the most advanced atomic clocks can drift, while the planet's journey remains steady. The regularity comes from the unchanging balance of motion and gravity. Unless something massive interferes, an orbit's rhythm is almost eternal. This is why ancient civilizations could predict eclipses and seasons with remarkable accuracy, guided only by the paths of the heavens. It's strange to think that every calendar, every birthday, every harvest festival is really just a marker in the great sweep of Earth's orbit. The planets are not just wanderers, they are timekeepers. Why ancient astronomers trusted the paths of planets. For early skywatchers, the stars were fixed, but the planets moved. These wanderers were mysterious, yet their motion followed a pattern that could be learned and trusted. Ancient astronomers tracked them night after night, mapping their positions, finding the cycles that repeated over years and decades. Knowing these patterns meant predicting the future, when the floods would come, when planting season would start, when certain stars would rise before dawn. For entire civilizations, the planets' steady orbits were a kind of promise written in the sky. Even without understanding gravity or inertia, they knew the planets would keep their appointments. And that trust, once earned, was never broken. The link between orbital motion and life on Earth. Our orbit isn't just a path through space, it's the stage on which all life here depends. The distance from the Sun, the tilt of our axis, the length of our year, all of these are products of our orbit. If Earth moved even slightly closer or farther from the Sun, the balance of temperatures would shift, reshaping climates and ecosystems. The predictability of our orbit gives life stability, seasons return in order. The sun rises and sets in rhythms life can adapt to. Without this stability, evolution itself might have taken a completely different course. In a way, life here is not just living on Earth, it's living within Earth's orbit. And the same is true for life on any world, anywhere. How seasons are written into the shape of Earth's path. Earth's orbit isn't a perfect circle, it's slightly stretched, an ellipse. This shape, combined with the tilt of our axis, creates the seasons. As we travel around the sun, the tilt changes the angle of sunlight hitting each hemisphere, bringing warmth to one side while the other cools. If our orbit were perfectly circular, seasons would still exist, but they'd be gentler. If it were more stretched, the difference between summer and winter could become extreme, possibly making large parts of Earth uninhabitable. The shape of our path is subtle, but it's enough to give us the rhythm of spring blossoms, summer heat, autumn leaves, and winter snow. In this way, the geometry of our orbit writes poetry in the language of weather and light. Why tiny shifts in orbit can change the climate. Over tens of thousands of years, Earth's orbit changes slightly. Its tilt, its distance from the Sun, and even the shape of its path vary due to gravitational nudges from other planets. These slow cycles, called Milankovitch cycles, have been linked to the timing of ice ages and warm periods in Earth's history. A small change in sunlight reaching a region, spread over centuries, can shift global climate patterns. The last ice age ended partly because of such changes. The next one, far in the future, will begin for the same reason. It's a reminder that our orbit is not just a backdrop to life, it's an active force shaping it. How planets carry the memory of their birth in their path. Every orbit is a kind of fossil. The distance a planet travels, from its star, the tilt of that path, the speed of its journey. All of these are shaped by the moment it formed. The early collisions, the dust cloud it emerged from, the gravitational shoves from neighbours, every event leaves a trace. Even now, Earth's orbit whispers about the time it was born. Its near-circular path tells us the young solar system had already calmed from chaos, but not completely. There are still tiny irregularities that hint at ancient turbulence. In this way, an orbit is not just a present-day reality. It's a record of the past, moving forward through time. And the planets carry those records in perfect silence, the fossil trails of past collisions and captures. Some orbits are scarred more visibly than others. A tilted path, an unusually stretched ellipse, or a moon moving in the wrong direction. These can all be signs of a dramatic past. They tell of collisions with massive bodies, close encounters with other planets, or even the capture of a wandering moon or asteroid. Mars's tiny moons, Phobos and Deimos, may have been captured asteroids, now trapped in their own miniature orbits. Neptune's moon Triton orbits backward, a clue it didn't form with Neptune but was pulled in later. These fossil trails are like fingerprints left behind in the cosmic dust. Even when the event is long past, the orbit remembers it, perfectly and forever. Why some orbits are tilted like secret signatures. Not all planets follow the same flat plane. In our solar system, most orbits lie close to a shared disk called the ecliptic. But some worlds, and many smaller bodies, travel on tilted paths, rising above and dipping below the common plane. These tilts are often the signatures of past events. A near collision, a gravitational nudge from a passing star, or the leftover angle from the way they formed. It's as though each tilted orbit carries a quiet mark saying, "Something happened here." These differences add depth to the solar system's structure, like the varied brushstrokes in a vast cosmic painting. How planets in other systems follow the same rules. When astronomers look beyond our sun, they find worlds orbiting distant stars. And though they come in all sizes and types, the same laws apply. Hot Jupiters, icy giants, rocky super-Earths, all are held in place by the same balance of motion and gravity. Some skim close to their stars in blistering fast orbits, others drift far out in the cold. Even in systems utterly unlike ours, where planets move in tangled, intersecting paths, the invisible handshake between speed and pull keeps them from flying apart. It's proof that these rules are not just local, they are universal, written into the fabric of space itself. The strange worlds that orbit in unexpected ways. Some planets have orbits so unusual they defy our expectations. There are worlds that loop around two stars at once, tracing huge figure-8 paths. Others move in extreme ovals, diving close to their star before swinging far into darkness. Some are tilted so sharply that their poles point directly toward the Sun for part of their year. These orbits can be the result of violent pasts, close encounters, captures, or even the migration of planets from one part of their system to another. Yet even in their strangeness, the same balance holds them steady. Their paths may be unconventional, but they are no less bound by the cosmic rules. How black holes keep their planets close forever. A black hole's gravity is unlike anything else. It's so strong that nothing, not even light, can escape once it crosses the event horizon. And yet, just outside that boundary, planets and stars can orbit just as they do around any other massive object. The same rules apply. Motion balances gravity, and the path is set. The difference is intensity. Around a black hole, the speed needed to stay in orbit is immense, and the closer you are, the faster you must move. Fall behind even slightly, and you're pulled inward, never to return. Despite their terrifying reputation, black holes can host stable, lasting orbits. Entire star systems may circle them in the quiet darkness. It's a reminder that even in the most extreme corners of the universe, the cosmic dance still holds. Why light itself bends around massive worlds. Gravity doesn't just pull on planets, it pulls on space itself. When a massive object like a planet, star, or black hole sits in space, it warps the fabric around it. Light, which normally travels in straight lines, follows these curves, bending as it passes. This bending, called gravitational lensing, can make distant stars and galaxies appear in multiple places at once, or stretched into beautiful arcs. Though planets bend light far less than stars, the effect is still there. A subtle bowing of the path that reveals their presence to careful observers. It's another sign that gravity isn't just a force. It's the shape of space telling everything how to move, the whisper of relativity in every orbit. Einstein's theory of general relativity refined Newton's laws, showing that gravity is not simply a pull, but the bending of space and time. This bending means that orbits aren't perfect loops carved in emptiness. They are paths traced along a curved landscape. Over long periods, this curvature causes tiny shifts in a planet's path, like Mercury's slow precession, which puzzled astronomers until relativity explained it. These effects are usually subtle, but they are constant, shaping every orbit in the universe. Even here on Earth, GPS satellites must account for relativity to keep accurate time. It's humbling to realize that our orbits are written not just in motion and mass, but in the very structure of time itself, how time runs differently on moving planets. In Einstein's universe, time is not absolute. The faster you move and the stronger the gravity you feel, the slower time passes for you compared to someone far away. A planet deep in a star's gravity well, or moving at high orbital speed, experiences time just a little more slowly than a distant observer. For Earth, the difference is tiny, but for worlds close to massive stars or black holes, the effect can be significant. This means two planets orbiting the same star at different distances are living in slightly different versions of time. It's a quiet, invisible shift, one you'd never notice in daily life, yet it's always there, woven into the fabric of the cosmos. The unending link between motion and the fabric of space. In the end, every orbit is more than just movement. It's a dialogue with the very shape of the universe. The path a planet takes is determined not only by gravity, but by the way space itself is curved by mass and energy. This is why planets follow predictable tracks, why light bends, and why time itself flows differently depending on where you are. It's as though the universe has written a set of invisible grooves into reality, and every moving body is simply tracing them. The planet's speed, the star's mass, and the curve of space combine into a pattern that can last billions of years. Why the universe's expansion doesn't break orbits. The universe is stretching. Galaxies are drifting farther apart as space itself expands. But here's the quiet truth, that expansion doesn't pull planets from their stars, or stars from their galaxies. The gravitational bonds within these systems are far stronger than the slow outward drift of space. It's like a drop of ink in water. The water may move, but the drop holds together because its molecules cling tightly. Planets remain bound to their stars, even as the universe grows around them. The orbits we see today are untouched by the grand cosmic stretching, locked in their own local harmony. Expansion rules the vast distances, but gravity rules the close bonds, the quiet tug-of-war between galaxies and their stars. While planets orbit stars, and stars orbit galactic centers, there's another layer of balance at play. The gravity of the galaxy holds its stars in place, just as the sun holds its planets. If the pull of the galaxy were weaker, stars could drift away into intergalactic space. If it were stronger, their paths would shrink inward. This balance is why our Sun and all its planets circle the Milky Way in a vast 230 million-year orbit. We are part of a much larger dance, moving through a galaxy shaped by countless forces. The solar system isn't just spinning on its own. It's being carried along on a greater journey. One motion nested inside another, like wheels within wheels. How our solar system drifts through the Milky Way. Our home in space is not fixed in one place. As the Sun orbits the center of the Milky Way, it carries the planets with it, moving through vast regions of interstellar space. We pass through clouds of gas, spiral arms of stars, and the gentle tides of galactic gravity. This drift doesn't disturb our orbits around the Sun, the local bonds are too strong, but it does mean we are always changing our cosmic address. The constellations we see today are not the ones our distant descendants will know. It's strange to think of Earth's orbit as part of a larger path, a small circle riding a grand, slow arc around the galaxy. A journey so long, no single human lifetime can measure even a fraction of it. The unseen currents of gravity in deep space. Space may seem empty, but it's full of invisible flows. Massive structures, clusters of galaxies, dark matter halos, create vast gravitational currents that guide the motion of stars and systems. We can't see them directly, but we feel their influence in the way galaxies move and in the gentle bends of light from distant objects. Our solar system is caught in these currents, moving not at random, but along unseen valleys and ridges in the fabric of space. It's as if the universe has carved hidden riverbeds, and we are drifting within one of them, carried along without ever knowing the edges. And yet, even in this vastness, our small orbit around the Sun stays steady, unbroken. Why the cosmic dance may truly never end. From the smallest dust grain to the largest galaxy, the rules are the same. Gravity pulls, motion resists, and together they create orbits, patterns that can last for billions, even trillions of years. The forms may change, stars may live and die, but the dance itself endures. Even when one chapter ends, a planet swallowed, a star fading, The pieces find new partners, new paths. The dance continues, reshaped but unbroken. Perhaps that's the most beautiful truth of all. In a universe of change, orbits are a kind of promise, not to stay the same forever, but to keep moving, to keep circling, to keep time alive. And somewhere above us tonight, in the quiet dark, that promise is being kept. The echoes of ancient orbits in today's night sky. When you look up at the planets tonight, you're not just seeing them as they are now. You're seeing the survivors of an ancient arrangement, still moving along the paths set billions of years ago. Each position, each alignment, is an echo of where they have been before, and where they will be again. Even the slow shifts and tilts of their paths are part of a repeating story. The night sky is a book that replays its chapters in endless cycles for anyone patient enough to read it. And those echoes will continue long after our own chapter closes. How orbits link us to worlds we'll never see. The laws that keep Earth in its place are the same ones guiding planets light years away. That means when we study our own orbit, we are also studying the structure of alien worlds, their years, their seasons, their possibilities for life. A planet orbiting another star may be invisible to our eyes, but by its pull and motion, we know it follows the same cosmic steps we do. This shared rulebook ties every world together like a silent agreement written across the universe. Even if we never visit them, we're already connected. The slow weaving of orbits into cosmic history. Over billions of years, orbits do more than move worlds. They weave the fabric of cosmic history. Collisions lead to moons, migrations shape climates, and stable loops allow life to flourish. Every twist in an orbit can set off a chain of events that shapes the fate of a world. In this way, the architecture of the solar system is not just a structure. It's a living memory, recording both the violence and the harmony that built it. And that memory is still being written, one silent lap at a time. The music of motion that never plays the same twice. If you could somehow hear the movement of planets, it wouldn't be a single repeating note. It would be a symphony, familiar in its rhythm, but always with small changes, quiet variations, and subtle improvisations. The planets keep time together, yet no two revolutions are ever exactly alike. It's the difference between hearing a song once and hearing it over a lifetime. The melody remains, but you notice new details each time. Space has been playing this music for billions of years, and it will keep playing long after we're gone. The horizon where orbits fade into mystery. Even with all our understanding, there is a point beyond which we cannot see. We can predict the paths of planets for millions of years, but beyond that, tiny uncertainties, the whispers of chaos, blur the picture. Someday, the dance will change in ways we can't yet imagine. Perhaps new worlds will join, others will drift away, and the shapes we know will become something else entirely. But whatever happens, there will always be motion, always gravity, always the pull and the glide. And somewhere, in the deep future, a night sky will shine over another world, wondering the same thing we do now. The unseen threads between all moving things. In the emptiness of space, nothing is truly separate. Every planet, moon, and star tugs on every other, however faintly. These tiny pulls add up over the ages, creating a web of motion that connects the smallest dust grain to the largest galaxy. Even your own body right now is pulling very slightly on the planets. A whisper of gravity too small to measure, but real nonetheless. It's humbling to think that in some unfathomable way, we're all part of the same silent network. How orbits turn chaos into harmony. At the beginning, the solar system was wild, a swirling, violent cloud of rock and gas. Yet over time, the collisions and the chaos shaped themselves into something ordered. The planets found lanes they could travel without crashing, and their speeds adjusted until they moved in sync. What began as a storm became a waltz, and in that waltz, there is enough space for each world to follow its own rhythm without disturbing the others. It's a reminder that even the most turbulent beginnings can lead to lasting balance, the patience of the cosmos in shaping paths. On human timescales, an orbit feels eternal, but in cosmic terms, it's just a slow breath. The changes that sculpt these paths happen over tens of thousands, even millions of years. The universe works with patience beyond anything we can grasp, moving worlds by the tiniest increments until they find their place. It's a different kind of time, one that doesn't hurry, yet never stops. And in that still, patient motion, worlds find their forever homes, the mirrors of our orbit in distant skies. Somewhere far away, another star has its own circle of worlds. They rise and set under alien suns, feeling seasons shaped by distances and tilts unlike our own. Yet their stability, their ability to keep time, to hold on to warmth, comes from the same balance we share. Our orbit is not unique, it's part of a universal language spoken by worlds we may never see. The same language that could be carrying life across the galaxy right now. The eternal promise in the turning of worlds. As long as gravity pulls and motion resists, there will be orbits. Stars will die, new ones will form, planets will be born from dust and drift into their own steady loops. The faces in the dance will change, but the dance itself will go on. There's comfort in that. The idea that even as everything changes, there's something constant, something reliable in the quiet turning of worlds. And somewhere above us tonight, that promise is being kept without a sound. The shared heartbeat of a solar system. Every orbit, every revolution is like a beat in the heart of the system. The planets move at their own paces, some quick, some slow, but together they create a rhythm. Jupiter's slow stride balances Mercury's swift loops. Earth's steady pace complements Neptune's long sweep. If you could hear this rhythm, it would be the softest drum in the universe. Steady, patient, never rushing. And it's a heartbeat that will continue for as long as the sun burns. The quiet resilience of planetary motion. Orbits are not fragile things. Even when disturbed, they bend, shift, and adjust rather than shatter. A passing asteroid might stretch a path, a neighbour's tug might tilt it slightly, but the planet still finds a new balance. This resilience is why the solar system has lasted for billions of years. The paths may change, but the motion continues, like a river finding new channels without losing its flow. It's a kind of cosmic stubbornness, the will to keep moving. How the smallest details keep the largest patterns alive. A solar system's harmony isn't just about big planets and strong pulls. It's about the fine details, the exact tilt of an axis, the precise timing of a resonance, the faint push of sunlight over centuries. These small things, almost invisible, keep the grand design from unraveling. Without them, the order might slowly dissolve into chaos. With them, the system endures. It's proof that in the universe, tiny influences can guard the greatest balances. The endless inheritance of motion. When one world is destroyed or captured, its momentum doesn't vanish, it's passed on. Fragments become moons, dust joins rings, debris finds new orbits. Motion is never wasted, it's simply redistributed, feeding the endless flow of the system. In this way, the death of one path becomes the birth of another. The dance doesn't stop, it evolves. And every new orbit carries with it a trace of what came before. The closing of one story and the start of another. Someday, our own orbit will change. The sun will age, the planets will drift, and the map of the solar system will be redrawn. But when that day comes, it won't be the end, just the beginning of a new chapter in the universe's great unending dance. Worlds will still turn, stars will still gather planets into their embrace. The balance between gravity and motion will continue in countless systems yet unborn, and somewhere another sky will shine and another storyteller will wonder why the planets stay in their orbits forever.